So let's do number 4. A hollow basketball. So what's the shape of a hollow basketball? If we look at, let's take a look at image with all of the moments of inertia. The table.
Sphere?
Yeah, is it a solid sphere or a spherical shell?
Spherical shell?
Right. Spherical shell means it's like a basketball. It just has the shell of it. It's in the shape of a sphere, but it's hollow inside. Okay, so that's why I specifically wrote hollow basketball in case you don't know that a basketball is full of air and it's just hollow inside. I wrote the word hollow so that it's more clear. Okay, so we have a hollow basketball, and if we look at the moment of inertia of it, it is 2/3 mr squared. Okay, so I'm just going to write the moment of inertia of a hollow sphere is 2/3 mr squared. So it has a radius of 18.8 centimeters, so 0.188 meters, and the mass is 0.210 kilograms. It's released from rest from the top of a 3.7 meter long ramp. So be very careful because sometimes it tells you that it's released from rest with an initial height of 3.7 meters or from a 3.7 meter high ramp, but this is 3.7 meters long ramp, so that means this length is 3.7. Whereas if it said it was a 3.7 meter high ramp, it would be referring to the height over here. Okay, so we need to find out what that height is. And it's inclined at 32 degrees, so we can do the same thing that we did previously with sine, with SOHCAHTOA, to find out what the height is. Let me just clean this up.
Isn't it the same idea also?
Pardon?
Isn't it the same idea of question 3 and 1?
Yeah, it's exactly the same thing. What is its velocity when it reaches the bottom? So we're looking for this V final here. Okay, so go ahead and do this question. It's the same thing. You're just using a hollow sphere moment of inertia rather than a disk or a solid sphere. They're all really similar to each other. Okay, and then you just have to be careful with whether the question's giving you the length of the ramp or the height of the ramp. So you can go ahead and do this question.
Okay.
You'll see, so there's 6 questions here, and you'll see that they're all very, very similar. Okay, so it's a very good indication of what you're going to see on your test. You're going to get something like this. The ball might be rolling down the ramp, it might be rolling up the ramp, but it's the same thing. It's just an energy conservation question, but something is rotating, so you need to use rotational kinetic energy in addition to just translational. Okay, I think we should start solving it together. So we're going to start the same way as before. So we'll say E total initial when the basketball is at the top of the ramp equals E total final at the bottom. So initially, when the ball is at the top, what kind of energy does it have?
Gravitational potential.
Right, so UG initial. And at the bottom, what type of energy does it have?
Translational and rotational kinetic.
Energy.
Perfect. So I'll just put in the equations, mgh initial, 1/2 mv final squared, and 1/2 I omega final squared. Okay, so we have the moment of inertia ready over here, the 2/3 mr squared. We also need the formula for V equals R. Are we going to replace the V or are we going to replace the omega?
Replace the omega.
Good, because we're looking for V. So we want the V. We want to get rid of omega. Omega equals V over R. So I'm going to sub the I and the omega into the formula here for I and omega. And then we can start cleaning it up. So I'll cancel away all the m's right now. And then the r's also cancel here. These r squared with this r, which is squared, will cancel. And then we can just rewrite everything. And then we can collect like terms. So we have 1/2 v final squared and 1/3. So we can multiply one side by 3/3 and the other side by 2/2, 2/2. So we have 3 plus 2, so 5/6. And now we can solve for v final. And then we can plug in. Are people getting the same answer?
Yeah, I did.
Yes.
Awesome. Any questions here? You'll see it's very, very repetitive.
Not from my side.
Okay. So there's not too many variations. There's changing the shape, which means the I is different. You just have to look at the table to find the I. And then there's whether the question's asking for V or omega. So if it's asking for V, you need to get rid of the omega. So change all the omegas to V over R. And if it's asking for omega, you have to change the V's to omega R. And then solve for the V. In the next question, it's slightly different. So we have a baseball. And here I wasn't super clear, but does anybody know what the shape of a baseball is? Is it a solid sphere or is it a hollow sphere?
Solid sphere.
Yeah, so on a test I'll be more clear, okay? So that you don't have to guess. So it's a solid sphere. So the radius is 8.3, the mass is 0.31. It's rolling along the floor at 3.7 meters per second. It comes to a ramp inclined at 32 degrees. How far up the ramp will the baseball roll? Okay, so this time the baseball starts at the bottom and it has an initial speed of 3.7 meters per second. And we're looking for the distance along the ramp that it rolls. So we're looking for this distance here. How far up the ramp? It's not asking for the final height. It's asking how far up the ramp. So that's the D. And that's what we're looking for. All right, let's start doing this question. So initially the baseball is at the bottom of the ramp, so it's on the floor. So we're going to say that the height at the bottom is 0. So what kind of energy does it have when it's at the very bottom initially?
Kinetic energy.
Kinetic energy, because
Yeah, good.
rotational and transitional kinetic.
Yeah, good. Perfect. And then what kind of energy does it have when it reaches its maximum height?
Gravitational energy. That's it.
Yeah, good. Okay, so formulas I'll start to put in. 1/2 mv squared, 1/2 I omega squared mgh. Okay, so now we're going to think about the v and the omega. Are we going to switch the v? So we have this formula, v equals omega r. Are we getting rid of v or are we getting rid of omega?
Getting rid of omega.
Yeah, because the question tells you that the initial speed is 3.7 meters per second. So that's the v. We don't know the omega, so we need to get rid of omega so that we can plug in v instead. So there's the omega. And then we have the I, moments of inertia for a solid sphere, which is 2 mr squared. And then we'll plug all of that in. Okay, now we can try simplifying a bunch of stuff. So the math is cancel, and then the r squared is cancel again. Remember that R is being squared because there's a square outside of the bracket. And now we can simplify everything. So we have 1/2, the initial squared plus the 2's cancel, so we have 1/5. The initial squared equals GH final. And when we add these, we still get 7/10, like the last one. The initial squared equals GHF. And we're looking for HF, which is 7/10 VI squared over G. And then we can plug everything in. So VI was 3.7. And then G is 9.8. And then getting 0.977857 meters, and that's at this height. That's the final height, 0.977857 meters. That's not what we're asked for though, we're asked for D. This is 32 degrees. So how are we going to solve for D?
The height over sine 32 will equal the D.
Yeah, so we're going to use SOHCAHTOA. So we'll say sine of the angle equals opposite over hypotenuse. And then we'll cross multiply. And then we'll solve for D. .85 meters. Yes, all right.